Hey guys, today I want to present a solution to the International Math Olympiad 1999 problem 4. At first, let's have a look on the problem statement. We are asked to find all positive integers x and prime numbers p such that x is less than or equal to 2p and x to the power of p minus 1 divides p minus 1 all to the power of x plus 1. At first, we want to take a look at the smaller cases and after that at the general case. We can see that if we take x equal to 1, then here the left-hand side is equal to 1, and here also the left-hand side is equal to 1. Therefore, for any value of p, these two equations are true. So we can take p arbitrary in this case. The second small case we want to consider is p equal to 2. Here we see that the left-hand side is just x, and on the right-hand side we have p minus 1, which is 1 to the power of x plus 1, is equal to 2. So we want to have that x divides 2, so x must be equal to 1 or 2, and we see then that this equation is also true then. And since we already have dealt with the case x equals 1, we have x equals 2 here as the only possible solution. Now we are ready to deal with the general case that x is greater than 1 and p is not equal to 2. We want to use this condition here in a clever way. And normally, when using divisibility arguments, it's easier to deal with prime numbers. But x is not necessarily a prime number, and therefore it's a good idea to consider some prime number q, such that q divides x, and we know that such prime q exists because x is greater than 1. Let's try to figure out some things about q. At first, I want to note that since p is not equal to 2, we know that p is odd, so p minus 1 is even, and therefore our right-hand side here is odd. This means that x is also odd, and therefore we can conclude that this prime divisor q here must be also odd. Moreover, since q divides x, we know that q also divides this right-hand side here, so we conclude that p minus 1 to the power of x is congruent to minus 1 modulo q, or if we square both sides, we get that p minus 1 to the power of 2x is congruent to 1 modulo q. Whenever we have the power of an integer congruent to 1 modulo a prime number, it's a good idea to consider the order of this integer modulo the prime number. So we want to define d to be the order of p minus 1 modulo q. Here I want to note that the right-hand side is only defined if q is not a divisor of p minus 1. But from this equation here, we see that this is indeed true. Using this equation here, we get that d must divide 2 times x. Moreover, we know by Fermat's little theorem that p minus 1 to the power of q minus 1 is also congruent to 1 modulo q. So we also have that d must divide q minus 1, and in conclusion we get that d divides the greatest common divisor of 2x and q minus 1. Remember that q is a prime divisor of x. If we now choose q minimal, we conclude that every non-trivial divisor of x cannot divide q minus 1, and therefore this greatest common divisor is equal to the greatest common divisor of 2 and q minus 1. Since q is odd, we conclude that this is equal to 2, and therefore we have that q divides p minus 1 to the power of 2 minus 1. This can be written as p squared minus 2p plus 1 minus 1, and this is now equal to p times p minus 2. Because q is a prime number, we know that q divides one of the factors of the right-hand side. But now, if q divides p minus 2, we see that in this equation here, the left-hand side is congruent to 1 and the right-hand side congruent to minus 1. But this is impossible since q is not equal to 2. Therefore, we conclude that q divides p. Using the fact that both of these numbers here are prime numbers, we conclude that they must be equal. At this point, we are ready to use this inequality here. At first, we have that p divides x, but x is less than or equal to 2p. Therefore, x must be equal to p or 2p. But we have already figured out that x is odd, and therefore we conclude that p is also equal to x. Right now, we only use the fact that p divides the right-hand side once. But indeed, we know that p divides the right-hand side p minus 1 times, and now we want to use this fact. In order to satisfy this condition, we must have that p minus 1 is less than or equal to the number of times p divides p minus 1 to the power of x plus 1. 1 can also be written as 1 to the power of x. And now we see that p divides p minus 1 plus 1 and that x is odd. Therefore, we are able to use the lifting the exponent lever to conclude that this is equal to nu p of p minus 1 plus 1 plus nu p of x. And here we see that this is just equal to 1. And since x is also equal to p, the second summand is also equal to 1, and therefore this is equal to 2. We conclude that p is less than or equal to 3, and since p is not equal to 2, we get that x must be equal to p equal to 3. Plugging this in, we see that 3 squared divides 2 to the power of 3 plus 1, and therefore this is indeed our last solution, and we are done.